Yeah, let's do this. We're doing this brain 3D viewer. Later, we hopefully be adding more fancy functionality to it, like labeling different components of the brain. Yeah, there's one annoying thing. Let's see which robot can fix this for us. Let's show this to, yeah, might need the GPT. I think it will change to GPT-4 as soon as you upload an image, wouldn't it? No, you actually have to select the model you want. Shall we use 4.0 or the original one? Can you look at this image? We're having an issue, for example, when scrolling using the mouse through the images. When moving up, it works fine, but when moving down, it actually scrolls the page itself instead of the slices within the 3D brain model. Let's see which robot can fix this for us.
To address the issue where scrolling down with the mouse scrolls the entire page instead of the slices within the 3D brain model, you'll need to capture the scroll event within the specific div or container where the 3D brain model is displayed and prevent the default behavior of the page scrolling. Here's a solution using JavaScript. 1. Add an event listener for the scroll event within the specific container. 2. Prevent the default behavior if the scroll is within that container. Here's an example of how you can implement this. 1. Modify your HTML to give an ID or class to the container displaying the 3D brain model. HTML div ID equals brain model container, your 3D brain model code here. 2. Update your JavaScript to handle the scroll event within this container. JavaScript document.getElementById brain model container.
Oh, actually, yeah, we're actually having GitHub Copilot doing changes to the code. Seem to understand what we want. Seem to have made some suggestions already. We have that volumetric. No, wait. Will prevent default. Which one? The volumetric view. No, we're actually talking about the other ones. Yeah, so GitHub Copilot didn't understand what we want just from these two lines of prompts. Let's try again. So we're looking at the canvas container. Okay. GitHub Copilot only fixed the volumetric view, which is the 3D model, which needs a lot of more work as well, but that's not currently what we are looking at. So waiting a scroller, canvas container. We have the wheel. Do we have the wheel event already? We must do. We only have the instructions. Sorry. Looking at the wrong file. Yeah, JavaScript. So we have the mouse navigation. Okay. So how do we change this code exactly? We found the location. Now we wanna. How do we change this whole code again? Yeah, prevent default. Let's try it out. And it actually works. Magic happens. Yeah, this one still works. Yeah, that one's a bit funny. Yeah, this one actually works now. We actually have another AI, GitHub Copilot, that is fixing the code for us, that does the actual coding. So if you can stick to general instructions, that will be great. We're having another issue with the fourth panel, with the fourth canvas called volumetric data. Well, first, the way it's panning is not great. It's hard to control with the mouse. It's like going all over the place. The focal point of it for it, I think, is not quite ideal. And second, also the way it looks like, there's something odd about it. We were trying to fix it last time, but we played with some of the parameters for rendering the volumetric data, but it still looks a bit odd. Can you make any suggestions for GitHub Copilot? How should it actually change the code? And it has the image of what was I looking at, but can actually give the same response but without the code. Again, as I said, we have another AI doing the coding for us. Can you confirm you understand?
Understood. Here are the general instructions without the code. General instructions for improving the volumetric data panel. 1. Control mouse behavior. Implement smooth and precise mouse controls for navigating through the volumetric data. Prevent the default scroll behavior of the entire page when interacting with the volumetric data panel. Adjust the focal point and sensitivity for mouse movements to ensure accurate control. Adjust rendering parameters. Fine-tune the rendering parameters to improve the visual appearance of the volumetric data. Set up the renderer with appropriate settings, including anti-aliasing and background color. Adjust the camera position and perspective to optimize the view. Add ambient and directional lighting to enhance the visual quality. Ensure proper loading and rendering of the volumetric data, focusing on achieving a clear and accurate representation. These instructions should help the other AI GitHub Copilot to generate the necessary code to improve the mouse control and visual rendering for the volumetric data panel.
Okay, we actually have GitHub Copilot generating something, but not the code. Generated pseudocode, but we don't want pseudocode. Are we using 3GS? Yes. Okay, so it's giving you like follow-up questions. How can we adjust the camera field view? Setting the FOV properly. Update the projection matrix. Here's an example. Why is it just an example and not the actual code? I don't know. Do we already have this, so it's giving us generic stuff? Hey, so how to adjust this code exactly? Let's see if it's still on topic. For improving mouse control and visual rendering. That's right. Mouse control and visual rendering. Mouse control is actually fine. There's nothing wrong with it. It's still generating a lot of stuff. The links actually work within GitHub Copilot, which is great. So we have this key down. Prevent default. We need lighting, camera position, volumetric data rendering, voxel size, so on and so forth. A downsample factor, a rotate speed. We don't have it. Where do we actually add it? Light intensity, darker gray background. Do we need a darker gray background? A prevent default scroll behavior. in the wheel event listener. The links seem to be wrong. Meant to be the event listener for this thing. Yeah, we already have prevent default. Enhance mouse control. Mouse control. So where do these settings actually go to in the code? Oh, this is, yeah, we don't want to go there. So we have the 3JS scene. We have the renderer, set color. Okay, the renderer. Configure the random background color. So we can do, let's just try if this actually works. Does work, but it doesn't make anything better. A directional light. Don't we have directional light? I don't think we have. No, we do have ambient light. Pretty sure this line of code will go there before we add ambient light. Then we have directional light, position, intensity, and we actually add it. That didn't change much. The original no, just loading for some time. What do we have? Controls, rotate speed. So that could go. A target set is zoom speed as if it's 4 or something. I think 1 was just fine, wasn't it? 1 was just fine. A rotate speed is 1 as well. Now this one, if we get rid of it, it's actually better. Okay, we actually improved quite a few things. The changes actually work, but the focal point, I don't know what is it called. Need to find the parameter for it. When I pan with the mouse, the center is not where I expect it to be. The other problem is that the vision for it, the overall rendering, is still not great. It doesn't look like a 3D model. Potentially, we might need some sort of mesh structure, what's called the filling around it, like essentially to show this where the skull is, and then later potentially have an option removing the skull. It's working much better. If you don't give it code, it does not generate any code. Improve rendering quality, mesh, structure of the skull, mesh, the skull, which can be toggled on and off. That would be great.
To address the issues with the focal point and rendering quality for the volumetric data panel, as well as adding a mesh structure to represent the skull, here are some general instructions for GitHub Copilot. Focal point adjustment. 1. Identify the center of the model. Adjust the focal point to be at the center of the 3D brain model to ensure smooth panning. 2. Use orbit controls. Ensure orbit controls is set to target the center of the model. Improve overall rendering quality. 1. Adjust rendering settings. Fine-tune rendering parameters such as lighting intensity and material properties to enhance the 3D effect. 2. Use a mesh structure for the skull. Load a mesh to represent the skull, which can be toggled on or off. Instructions for GitHub Copilot. 1. Focal point adjustment. Ensure the orbit controls target is set to the center of the 3D brain model. Calculate the center of the volumetric data and set it as the target for the controls. 2. Improve rendering quality. Adjust lighting intensity and material properties to improve visual appearance. Use a mesh material to better define the 3D structure. 3. Add skull mesh. Load a mesh representing the skull from the volumetric data. Provide an option to toggle the visibility of the skull mesh. Detailed suggestions. 1. Focal point adjustment. Ensure orbit controls targets the center of the brain model. Calculate the center coordinates of the volumetric data and update the controls. 2. Lighting and material adjustment. Fine-tune the ambient and directional lighting for better illumination. Use appropriate material properties to enhance the 3D effect. Skull mesh. Load and render a skull mesh from the data. Add controls to toggle the visibility of the skull mesh. Example configuration points. 1. Set focal point in orbit controls. Target the center of the brain model. 2. Adjust lighting. Use higher intensity for better illumination. Ensure appropriate color and contrast settings. 3. Load skull mesh. Use appropriate 3D model loading mechanisms. Provide options to toggle skull visibility. These adjustments should help GitHub Copilot generate the code to improve the focal point handling, enhance the overall rendering quality, and add a mesh structure for the skull.
Yeah, we already have intensity. Ambient line intensity is set to 0.5. Just remove it here. Yeah, we had this error before. How do we integrate this change and rewrite the whole script? I'm having trouble integrating. Let's see if it can actually help. Yeah, we need to find the center of that model as well. It regenerated the code for us. Let me. How is it so much shorter? Does the skull bit? What? I might need to rewrite the whole thing. Why are we loading? It's just that the 3GLTF loader is not available in the current scope. Yes, because we're using a different one, 188. Why don't we have it? And if I need to load it, don't I do it from the HTML code? It is part of the 3JS library. We can add it inside the HTML. Have the orbit controls. Okay, how do I change the code exactly to include it? Why is it telling me? If your Flask application Axial slice number, okay. Yeah, this is what's serving the slices backend. Don't think it understood what the problem might be. So the other AI made some changes, but then we're getting an error. I don't think it understood what the what are we trying to do, uh, which is fix the volumetric 3D model. If you can give a bigger picture as well, that will be great. If you have any jokes, go for it, but keep them relevant to the topic. Try to deliver them. Deploy. So the volumetric data loaded successfully, but still I see some rubbish. I don't like it going into coding mode. Why did the 3D brain model go to therapy? Because it has too many unresolved. Oh, come on. No. I'm amazed that the Python JavaScript code just works, but then other things are just horrendous. Choose a master direction like panning, zooming, and rotating a smooth and precise. Improve a rendering quality. So this is all happening in JavaScript. Focal point adjustment, rendering quality. Calculate the center. Yeah, that sounds. Can we do it in the code? We will be loading different models, so we'll need to calculate the center of the model every time so the panning is correct. After the volumetric data is loaded, still generating. I don't know what's jumpy like that. That's still generating stuff. A volumetric data loaded successfully. Voxel size, geometry, buffer geometry, position, down sampling factor of 1. Initiate min-max for each axis to calculate the center. Okay, we definitely need that. Okay, how do we rewrite this bit and integrate the last change? Well, what do you know? It actually works. So we're calculating the center of the volumetric data, and now when panning in and out, it's actually when loading the page, it's actually in the center. That's nice. But it still doesn't look like a 3D model. I suspect that's because normally you would just display okay, GitHub Copilot actually fixed the code based on your instructions, which is great. Can we move on? Can we explain why the 3D model of the volumetric data looks like that? It's a bit crude, to say the least. It doesn't look like what I normally used to see for this fourth panel when reviewing MRI data. Can you give a bigger picture and some potential instructions for Copilot to change the code? I added two images so you can see what I see, but also the difference between the first and second image is the different panning of the 3D volumetric model.
Understanding the crude look of the volumetric data. The 3D volumetric model in your MRI viewer appears crude because of several potential issues. 1. Low resolution or insufficient data points. The volumetric data may not have enough resolution or data points, leading to a blocky or pixelated appearance. 2. Improper rendering techniques. The rendering method may not be optimal for volumetric data, lacking smooth interpolation between points. 3. Lighting and shading. Insufficient or improper lighting can lead to a flat appearance without depth perception. 4. Color mapping. The color mapping may not accurately represent the different tissues or structures within the brain. Big picture solution. To improve the quality of the volumetric data rendering, you need to 1. Increase data resolution. Ensure that the data being used has a high enough resolution. 2. Improve rendering techniques. Use better rendering techniques like trilinear interpolation or volume rendering shaders. 3. Enhance lighting and shading. Implement more sophisticated lighting models, including ambient, diffuse, and specular lighting. 4. Apply accurate color mapping. Use appropriate color mapping to highlight different structures clearly. Instructions for GitHub Copilot 1. Increase data resolution. Ensure that the volumetric data has a high enough resolution. If downsampling is applied, consider reducing the downsampling factor. 2. Improve rendering techniques. Implement trilinear interpolation for smoother transitions between data points. Use volume rendering shaders to better represent the 3D nature of the data. Enhance lighting and shading. Add ambient, diffuse, and specular lighting to the scene to create a more realistic appearance. Adjust the intensity and position of the lights for better depth perception. 4. Apply accurate color mapping. Use color mapping that accurately represents the different tissues and structures in the brain. Consider using transfer functions for better visual differentiation. Detailed instructions for Copilot. 1. Increase data resolution. Ensure high resolution for the volumetric data and reduce the downsampling factor if necessary. Implement trilinear interpolation. Use trilinear interpolation to smooth out the voxel transitions. 3. Use volume rendering shaders. Implement volume rendering shaders to better represent the 3D structure. 4. Improve lighting and shading. Add ambient light to the scene. Use directional or point lights with proper intensity and positioning. Implement Phong or Blin Phong shading for better visual effects. 5. Apply accurate color mapping. Use appropriate color maps for different brain structures. Consider using transfer functions for enhanced visualization. Summary of steps for Copilot 1. Increase data resolution. Ensure the data used has a high enough resolution and reduce the downsampling factor. 2. Improve rendering. Implement trilinear interpolation and volume rendering shaders. 3. Enhance lighting. Add and adjust ambient, diffuse, and specular lighting for better depth perception. Number 4. Apply color mapping. Use accurate color mapping to differentiate brain structures. These instructions should help GitHub Copilot generate the necessary code to enhance the visual quality of your 3D volumetric model.
Yeah, so I would like to actually improve this. Yeah, I would also like to fix the size of the fourth panel. Can we fix the size of the fourth panel? See if it understands which one is it. Yeah, volumetric view, that's right. We have set size. What if we get rid of it. Well, that just solved the problem. And what if we bring back the dark background? Okay, that works as well. Okay. Any errors? Is an error. Still getting that error. Oops. That's something. A GitHub Copilot should be able to resolve. I thought we fixed. Oops. I think we forgot. F3JS. Uh, which one should we use? Is that one working at all? Include GF loader. We don't have it. It's the GLTF model. Before we move on to other stuff, we need to fix this error. Can you explain what's going on? Give a bigger picture and potential solutions. Yeah, it's something to do. Okay, in JavaScript, we need to make sure. Do we do any imports? I don't know why. Why are we doing import in JavaScript? Yeah, we don't have the skull. That will also be a problem, wouldn't it? It's just part of 3JS. Yeah, now we are going places. We don't actually need this. Why are we trying to import libraries from within JavaScript? Can we just do it once in HTML? Okay, in HTML. Yeah, we updated the HTML. We don't currently have the model. a problem. Still having a problem with importing libraries and things. And let's try compile it to specific error. I suspect one of those. None of them exist. None of these links, just hallucinated links. Why are you hallucinating links at me? Okay, GitHub Copilot suggesting different links. So this would be instead of 3JS. This one actually works. Yeah, that's better. That is better. So don't use that one ever again. Don't know why. Don't know why it's suggesting that. Yeah, we're having trouble with the orbit. Can we fix the other links as well? These links are not working. There's the problem with those CDNs. Okay, now it's suggesting in commenting in HTML. Horrible, horrible, horrible. Because it has stuff in the beginning and end. Big no-no. Don't understand. Don't understand. Again, the GLTF loader and the orbit controls JavaScripts are not working. The links in HTML didn't work correctly. So can we find working links? Or fix the code in another way? I don't particularly understand why do I have to install 3 as opposed to just getting the JavaScript code from a public repository or a CDN.
The issue with the GLTF floater and orbit controls not working correctly from the CDNs may be due to incorrect paths or the specific version not being hosted on those CDNs. We can address this by providing correct links or self-hosting the necessary files. Correcting the links or self-hosting. Here's how you can fix the issue. 1. Use correct links. Find correct links for the scripts. 2. Self-host the files. Download the scripts and host them locally if correct links are not available. Step-by-step solution. 1. Use correct links from CDNs. Update the script links with correct URLs if available. Here are the correct URLs from a reliable CDN. HTML include 3.js. Script circle https://cdnjs.cloudflare.com ajax/lib/3.120s/r120s script. Include gltf/cdnjs.flare.com/age-lib/3.js/wars example/js/loaders gltf loader. Include orbit controls cdnj@cloudflare.com/ajax/libs 3./controls/control/orbit-contrib2. Self-host the files. If the above URLs still do not work, you can download the necessary files and host them locally. Download the files: gltfloader.js, github.com/mr3.js/blar1/example.js/loaders/gltfloader.js or/mrdoob/3 examples/controls/orbit controls. Place them in your project. Put these files in your static JS directory or another directory within your project. Include them in HTML. HTML include 3.js script/cdn.cloudflare.com/ajax/r128//screen. Include gltf loader from local files, script/static.js. Include orbit controls from local files, static.js/orbit controls. Example HTML. Here's the complete HTML example with local hosting. HTML Donkin head, meta charset UTF-8. Meta name viewport content width device width, initial scale 1 point title 3D brain MRI viewer, body. Includes canvas volumetric view.canva.js. Include 3.js. Scripts are cdnjs.cloudflare.com/ajax libs3 ed/3s/r128 /ltf loader from local/static/js /ltf loader. Include orbit controls from local files /orbit controls.path to your/main.javascript. Example JavaScript. Main.js. Ensure your JavaScript uses the globally available 3 gltf loader and orbit controls. JavaScript function load skull mesh, const loader equals new 3 gltf loader, loader.load path to skull slapmodel.gltf, funcgltf, scene.add, gltf.scene, undefined, function error, console.error. Example of setting up the scene, camera and renderer, const scene equals new 3.scene, const camera equals new 3 perspective camera, 75 window.innerwidth slash window.innerheight 0.1 1000, const renderer equals new 3.webgl renderer, renderer.set size win.innerwidth win.innerheight, document body.append child renderer DOM element. So example of using orbit controls, const controls new 3.orbit controls camera, renderer.dom element, controls.target set 000, controls.update, slash function call to load the skull mesh, load skull mesh, render loop function animate, request animation frame animate, controls.update, renderer.render scene camera, animate. Summary. 1. Use correct CDN links. Ensure the URLs for GLTF loader and orbit controls are correct. 2. Self-host the files. Download the scripts and include them locally if necessary. 3. Update HTML. Include the scripts in the correct order in your HTML. By following these steps, you should resolve the import issues and get GLTF loader and orbit controls working correctly in your project.
Okay, we downloaded the necessary JavaScript code locally, so it's in JS static folder. Moving on, we now have, well, kind of obvious, but we now have the issue that we don't have the skull model. Now, what was the idea behind it? Were we meant to generate it out of existing data? Is that correct? It's only me, or it looks worse than it used to be. Again, can you regenerate the same response but without the code? We have GitHub Copilot that we still would like to use, that will be doing the actual coding. So just stick to the bigger picture. Still can look at it. Yeah, we need to pre-process essentially the MRI data. Don't understand. Wasn't this all meant to be in the original Nifty file? Let's read
Generating
this.
a skull model from MRI data. Overview. To generate a skull model from MRI data. 1. Pre-process MRI data. Segment the skull from the MRI data using pre-processing techniques. 2. Create a mesh. Convert the segmented skull data into a mesh format. 3. Load and render. Use Three.js to load and render the skull mesh. Detailed steps. 1. Pre-process MRI data. Segment the skull. Utilize image processing libraries, e.g. Nbabel, NumPy, scikit-image in Python to identify and extract the skull from the MRI data. Export the segmented data. Save the extracted skull data as a 3D model in a format like .obj or .stl. 2. Create a mesh. Generate the mesh. Convert the segmented skull data into a 3D mesh using tools like MeshLab or Blender. Save the mesh. Save the resulting mesh in a format compatible with Three.js, such as .gltf or .obj. 3. Load and render the mesh. Use Three.js. Load and display the generated mesh in your web application using Three.js. Instructions for GitHub Copilot. 1. Pre-process MRI data. Implement code to load MRI data, segment the skull, and export the data as a 3D model. 2. Create a mesh. Convert the segmented skull data into a 3D mesh and save it in a compatible format. 3. Load and render. Write the Three.js code to load and render the skull mesh. Hash summary. 1. Pre-process the MRI data. Segment and export the skull from the MRI scans. 2. Create a mesh. Use tools to generate and save the mesh. 3. Load and render. Implement Three.js code to visualize the mesh. These steps will help GitHub Copilot generate the necessary code to create and display a skull model from MRI data.
So we do have a pre-processing Python script. You can see it in the middle window of the image attached. Now originally we had like the nifty file. We also have inspect nifty Python script that I'll show you the output of this file below, and can you let me know if the what data exactly is already in that data file, and why do we have to do so much pre-processing to display it correctly? A bigger picture is fine. Can you quickly give me the summary of the last response, and also any use of actually using the inspect NIFT Python script to put it in line in our all processing, because surely that should help the rendering. This is the code that used to generate the header and the shape of the data, etc. Can we use it in our pre-processing, and eventually in the front end?
Quick summary of the last response. 1. Data in if file contains 3D volumetric MRI data with dimensions 236 by 256 by 256. Voxel values are 16-bit integers, with each voxel approximately 0.8 millimeters by 0.8 millimeters by 0.8 millimeters. Includes transformation matrices for aligning voxel data within 3D space. 2 preprocessing goals: slice generation, convert the 3D volume into 2D slices for visualization. Volume data conversion, create a web-friendly format, e.g. JSON, of the 3D data for rendering. Segmentation and mesh generation, extract specific structures, e.g. the skull, and convert them into 3D meshes for detailed visualization. Using inspect.nif.py in preprocessing. The inspect.nif.py script can be integrated into your preprocessing workflow to provide crucial information about the inifd file that can assist in rendering and processing. Integration steps. 1. Incorporate header information. Use the header information to understand the dimensions, voxel sizes, and transformation matrices. This information can be essential for accurately rendering the data in the front end. 2. Utilize data shape. Knowing the shape of the data helps in segmenting the data accurately and creating 2D slices and 3D models. Updated preprocessing script. Here's how you can integrate the inspect.nif.py functionality into your preprocessing script. Preprocess script with integrated header information. Python import nibubble as nibi, import numpy as np, import os, import matplotlib.pyplot as plt, import json, def inspect nifty file, img equals nib.load nifty file, header equals img.header, data shape equals img.getFdata, shape return header, data shape, def create slices in volumetric nifty file, output dir img equals nib.load nifty file, data equals img.getFdata. Create output directories if they don't exist. Axial dir equals path join output dir axial. Sagittal dir equals os path join output dir sagittal. Coronal dir equals os path join output dir coronal. Volumetric dir equals os path join output dir volumetric. Os.make dirs axial dir exist okay true. Os.make dirs sagittal dir exist o true. Os.make dirs coronal dir exist o true. Os.make volumetric dir exist okay equals true. Save slices for I in range data.shape, plt.imsave.path join axial dir f2png np.rot90 data cmap equals gray. For I in range data shape, pl.imsave path join sagittal dingy np.rot90 cmap equals gray. For I in range data shape 1, pl.imsave path join coronal dir np.rot90 cmap equals gray. Save volumetric data as a JSON file with openos.path volumetric dir volumetric.json w as f. json.dump data.tolist f. If core name equals main, nifty file equals sub0ses t1w.nii. Output dir equals static /data. Inspect NIFTI file header, data shape, inspect nifty file. Print header, print data shape. Create slices and volumetric data, create slices and volumetric, nifty file, output dir. Using header information in front end 1, rendering. Use voxel dimensions and transformation matrices to correctly position and scale the 3D model in the viewer. 2, visualization. Utilize slice information to provide accurate and interactive 2D slice views. Summary. Integrate header information. Use the inspect NIFT PI functionality to gather essential metadata about the NIFT file. Enhanced preprocessing. Generate 2D slices and volumetric data using the updated preprocessing script. Accurate rendering. Use the collected metadata to improve the accuracy of the 3D model rendering in the front end. These steps will ensure that your MRI data is pre-processed correctly and rendered accurately, improving the overall quality and interactivity of your 3D brain MRI viewer.
Okay, I'm not sure if the model was improved significantly or not. Probably not. Sorry, the data is the same data, but I'm saying I'm not sure that the pre-processing, the different pre-processing code made any significant improvements. It doesn't look like. But also, as you can see from the image attached, we're obviously getting an error because we do not have the skull model. So how do we go about it?
Steps to generate and use a skull model from MRI data. 1. Preprocess the MRI data to segment the skull. Segment the skull. Extract the skull from the MRI data using an image processing library. Generate the mesh. Convert the segmented skull data into a mesh format. 2. Create the mesh using a tool like MeshLab or Blender. Use a tool like MeshLab or Blender to convert the segmented data into a 3D mesh. Save the mesh in a format compatible with Three.js, such as .obj or .gltf. 3. Load and render the skull mesh in Three.js. Ensure the mesh file is correctly loaded and rendered in your Three.js application. Detailed instructions. 1. Segment the skull and generate the mesh. 1. Segment the skull in Python. Use libraries like nebabel, numpy, and scikit-image to segment the skull. 2. Export the segmented data. Save the segmented skull data as a 3D model in a format like .obj or .stl. Example process. Load MRI data. Apply thresholding or other segmentation techniques to extract the skull. Use marching cubes from schemage.measure to generate a mesh. Create the mesh using MeshLab or Blender. 1. Load the segmented data into MeshLab Blender. Import the segmented data into MeshLab or Blender. 2. Generate and export the mesh. Convert the segmented data into a 3D mesh. Export the mesh in .ij or .gltf format. 3. Load and render the skull mesh in Three.js. 1. Ensure the mesh file is available. Place the generated mesh file in the appropriate directory static/models. 2. Update Three.js code to load the mesh. Use gltf loader or obj loader to load the mesh. Steps to implement. 1. Update the preprocessing script. Segment the skull and save it as a 3D model. 2. Generate the mesh with MeshLab or Blender. Load the segmented data, create the mesh, and export it. 3. Update Three.js to load the mesh. Ensure the mesh file is in the correct directory. Modify Three.js code to load and display the mesh. Summary. 1. Segment the skull, extract the skull from the MRI data, save as a 3D model. 2. Create the mesh, use MeshLab or Blender to convert the segmented data into a mesh. 3. Load and render in Three.js, place the mesh file in the appropriate directory. Update Three.js code to load and render the mesh. These steps should help generate and integrate a skull model from your MRI data into your 3D Brain MRI viewer. Based on your workflow and the information provided, it appears you did not explicitly mention or use BrainDir in the pre-processing steps described. BrainDir is a tool for automatic brain extraction and cortical surface reconstruction, which can be very useful for pre-processing MRI data, especially for tasks like skull stripping. Should you use BrainDir? BrainDir can be particularly useful for skull stripping, removing non-brain tissues from the MRI scans, which is essential for accurate brain imaging and visualization. Cortical surface reconstruction, generating accurate models of the brain surface, which can be used for advanced visualizations and analyses. Integrating BrainDir into your workflow. If you decide to use BrainDir for pre-processing your MRI data, here's how you can integrate it into your workflow. 1. Install BrainDir. Ensure you have BrainDir installed on your system. Follow the installation instructions provided in the BrainDir repository /github.com/braindir/braindir. 2. Pre-process the MRI data with BrainDir. Use BrainDir to pre-process the MRI data, focusing on skull stripping and cortical surface extraction. 3. Generate the skull model. Once BrainDir has processed the data, you can use the output to create a 3D mesh of the skull. Example workflow with BrainDir. 1. Pre-process MRI data with BrainDir 1. Run BrainDir. Use BrainDir's command line tools to pre-process the MRI data. Example command, bash BrainDir input sub 0ss1t1w.nii output directory. To verify the output, ensure the output includes the skull stripped brain and any other required files. To generate the skull mesh, 1. Convert the process data. Convert the skull strip data into a mesh format using a tool like MeshLab or Blender. 2. Save the mesh. Export the mesh in a format compatible with 3.js, .obj, or GLTF. Hensharsh 3. Load and render the skull mesh in 3.js file. Ensure the generated mesh file is located in the appropriate directory, statics models / 2. Update 3.js code. Modify your 3.js code to load and render the mesh using GLTF loader or OBJ loader. Summary. Integrating BrainDir. 1. Install and use BrainDir for skull stripping and cortical surface reconstruction. 2. Generate skull mesh, convert processed data into a 3D mesh. 3. Update 3.js, load and render the generated mesh. Using BrainDir can significantly improve the pre-processing of your MRI data, making it more suitable for accurate and detailed 3D visualization. If you have not already, consider integrating BrainDir into your pre-processing pipeline for better results.
Yeah, so including ChatGPT as an author for all this stuff. It hallucinated a bit before with references. It's actually not GPT-4, it's GitHub Copilot. Have to fix it. Yeah, we have so this data is coming from openneuro.org. This is what the website looks like. Hopefully it stays there. It's a really good resource. Some of the data sets are, yeah, I've seen before a Creative Commons 0, meaning no attribution is required. Obviously you should put an attribution. All my stuff is Creative Commons attribution 4. Yeah, so just use it as you wish. Do mention the where you got it from. Fixing targets visual search, the role of dorsal and ventral attention networks in the processing of relevance and rarity. Okay, that's interesting. That's only from 5 days ago. I think last time to find that example, I mean, pretty much anything will do, but yeah, we filtered it by activity. Was this flanked task? I don't remember that one. Can you recognize the files based on this accession number? Not sure. It's a pre-process thing. No, it only has the subject. There's nothing in the header that seemed to indicate where this data came from. So that's unfortunate, but classification learning sounds interesting. What makes those activity? Right. Yeah, you have yeah, that many downloads. It's quite a lot, isn't it? And what is this task? It's back from 2016, updated 2018. It's just can we find something more recent? fMRI audio visual valence congruence, whatever that means. A visual object recognition, that could be interesting, assuming the objects are there as well. Okay, now we're talking face processing EEG data for EEG lab. Okay, doesn't matter if it's EEG lab or not, is it? But what's interesting about this one is that it supposedly has both EEG and MRI data in it, which we are highly interested in. Right, we have was it 20 subject, we have the images, and the good thing about this website is that yeah, must be downloaded to view. It's an image, right? Okay, have some .mat, so MATLAB files, codes. We might ignore them for now. Let's go to some random patient. So we have anatomy and EEG in JSON files. That's interesting. Can we actually view them? No, because it's actually it's not the actual data 1010 system. So it's a high resolution. It's supposed to 1020. It has double the electrodes. So it's actually very, very interesting. And yeah, Creative Commons 0. So you don't see that often. Good on them. On the thank you authors for making this available. Let's check. Yes, so how do we work with one of those data sets? So we have the MRI. It's a compressed nifty file. We know that much. And the good thing about OpenNeuro is that it has a code that just loads the data. I don't know what that is. Some sort of artifact. They removed the face, I guess, for privacy reasons. This is really, really nice. And how is it so bloody quick as well? Very nice. Don't often say that. Yeah, and you can see, yeah, so yeah, that's the thing with this model as opposed to what we have. Yeah, we don't have those red lines. Yeah, which are actually quite useful. For example, you can focus on stuff. See what on earth. Yeah, you can use the mouse scroller as well. Just curious what that is. I don't think there's anything special about the brain. I don't know. UK Medical Research Council and Electa, some corporate influence there. But I mean, the data is there. It's from 2021, so 4 years ago. The thing is, how to download. Download with Datalad, with Node.js, download from S3, download with your browser. We like the browser, don't we? We like the browser. And I'm not logged in or anything. This was which patient? Yeah, subject 9, anatomy. It's 22.7 megabytes, the compressed nifty file, and it's just downloading in no time. That's very, very, very nice. Thing is, I'm not sure if my thing can deal with compressed data or not. And I'm really wondering, how is this? Oh, meant to open it in another tab. Open in another tab. This one just has a viewer and it just works. It's really fast. Can we check F12 how it works? If we refresh the page, we can use, yes, on any website. Can refresh the page and see what's actually running. So that is just some logo. We're actually looking for any JavaScript files. Events, there's some sort of validation. It was this is some sort of font. A Google APIs, I don't know why. Okay, config J. Config JS. Doesn't look like this will be doing. The second finger from the radial side of the hand next to the thumb. Lower part of the arm between the elbow and the wrist. Description. What are those? Nose, teeth, cheek, chin. So it's nice, but how are they actually being used? And independently existing thing, living or non-living. What? Biological. An entity that is biological that is related to living organism. Okay. Bilateral. In library generated periodic discharges. Spike and slow wave morphology. Epileptiform interictal activity. Okay, what is this file? What is this file? It's way too long for me to pop into. Is this what's. I don't think this is what parsing the. I think this is what parsing the Nifty file. Can save. Just so we can view it a bit better. Google tracking. Yeah, Google is everywhere. Hey, downloading from the website is fine. What else is loading? A font. Don't know what that is. Yeah, Google. Yeah, it's doing Google Analytics. I don't know why. Okay, whatever. Open Neuro SVG, some SVG file. Okay, it's a lot to it. Now SVG, a CSS. Another Google Analytics file. GraphQL. A GraphQL. Open Neuro GraphQL. Sandbox. There's some sort of sandbox environment. That's interesting. Schema. Go to graph. This one is requiring. Yes, it's some sort of third party thingy. We're doing this for educational purposes, not trying to hack the website or anything like that. Of course, yeah, we have this JavaScript fresh desk. It's a third party something. Don't know what it is. Now a fresh desk. I assume it's not relevant. Fresh desk, fresh desk, fresh desk. Font, font, font. Fresh desk, Amazon, AWS, okay. A GIF image. SVG. Deface. Right, so they're actually loading. I don't know, that's actually what the file is called. That is the original file. It's called deface something because they removed the face. That's fine. Amazon, Open Euro, and again, I'm curious. Looks like the same file. Don't know why it's loading it multiple times. I'm essentially looking for the JavaScript code that does this rendering. And let's see. That's the HTML. Container, background, no color. Font, Google, tag manager. They're using a lot of Google tracking and the like. I don't know why, but okay. Okay, I think this might be, yeah, that's the one we have we copied already. I think that's the main, that's what's doing the rendering, but I'm not 100% sure. Not 100% sure. Not 100% sure. Very interesting though. Very interesting. Okay, question. How is the nifty file on openneuro.org is loading so quickly? You can view, pan, zoom. How's it all happening? There's this very long JavaScript code. Is it what rendering the data? The original data is also seem to be still compressed. Can you also explain the images? What's the structure of the openneuro.org 3D brain viewer? It's the file display. And it's just taking the compressed image. So how is it able to do it all so quickly?
Hash how openneuro.org loads and renders nifty files quickly. Key components and techniques. 1. Efficient file handling. Compressed file format. The .nii.gz file is a compressed nifty file, which reduces the data size and speeds up file transfer. Streaming and lazy loading. The data might be streamed or lazily loaded, allowing the initial parts of the file to be used immediately without waiting for the entire file to be downloaded. Ver2 WebAssembly WASM. WebAssembly modules. Often heavy computations for medical imaging are offloaded to WebAssembly, which allows running compiled code in the browser at near native speed. 3. Efficient data structures and rendering. Efficient parsing. The data is parsed efficiently using optimized JavaScript libraries. WebGL and GPU acceleration. WebGL is used for rendering, leveraging the GPU for fast visualization. 4. Optimized JavaScript libraries. Libraries like cornerstone.js and anyview.js are designed for medical imaging and provide fast, interactive rendering capabilities. The long JavaScript code you see likely includes these libraries and custom logic to handle the data loading, parsing, and rendering processes. Structure of openneuro.org 3D Brain Viewer. 1. Front-end components. JavaScript libraries utilizes specialized libraries for medical imaging, e.g. cornerstone.js, NiView.js. WebGL for rendering uses WebGL to render 2D slices and 3D volumes interactively in the browser. WebAssembly, WASM may use WASM for computationally intensive tasks, enhancing performance. 2. Data handling. Compressed data uses .gz files for efficient storage and transfer. Streaming streams data to allow for quick interaction without needing to load the entire file at once. 3. Interaction capabilities. Pan and zoom provides interactive tools for panning and zooming. Slice navigation allows users to navigate through different slices of the MRI data. Example workflow of how openneuro.org might work. 1. File request. The user requests a .nii.gz file from the server. The file begins to download, and if streaming is supported, the data is processed as it arrives. 2. Data decompression. The compressed .ni.gz file is decompressed in the browser using JavaScript or WebAssembly. 3. Data parsing. The nifty file is parsed to extract header information and image data. Libraries like nifty-reader.js can be used for parsing the file. 4. Rendering. The data is fed into a rendering engine, e.g. WebGL. For 2D slices, each slice is rendered on a canvas element. For 3D volumes, the data is mapped into a 3D texture and rendered using volume rendering techniques. 5. User interaction. Users can interact with the rendered data using mouse or touch events. The interaction logic, pan, zoom, slice navigation is handled by JavaScript code. Explanation of openneuro.org interface. 1. File display. The interface displays the file with options to pan, zoom, and navigate through slices. The compressed.nii.gz file is decompressed and parsed on the fly. 2. Rendering. 2D view displays axial, sagittal, and coronal views of the MRI data. 3D view renders a 3D volume if supported. 3. Performance optimization uses WebGL for hardware-accelerated rendering, streams data, and uses efficient parsing and rendering techniques to ensure smooth interaction. Conclusion: openneuro.org achieves fast and interactive visualization of nifty files by leveraging modern web technologies like WebAssembly, WebGL, and efficient JavaScript libraries designed for medical imaging. These technologies work together to handle large datasets, provide fast rendering, and allow for smooth user interactions. If you are looking to implement similar functionality, consider using libraries such as cornerstone.js, NIView.js, and leveraging WebAssembly for performance-critical tasks. Additionally, ensure your data is compressed and use streaming techniques to improve load times and interactivity.
Okay, so how do I need to change or update my code for it to work as fast and furious as this one?
To achieve performance similar to openneuro.org, you can incorporate several optimizations into your current workflow. Here are the steps you can take. Steps to optimize your MRI viewer. 1. Use efficient file formats and compression. Use .ini.gz files to ensure that the data is compressed, reducing load times. 2. Implement streaming and lazy loading. Stream data in chunks or use lazy loading to start rendering parts of the data before the entire file is loaded. 3. Leverage WebAssembly WASM for intensive computations. Use WebAssembly to handle decompression and parsing of the nifty files in the browser. 4. Use optimized JavaScript libraries. Integrate libraries such as cornerstone.js and anyview.js for efficient medical image visualization. Ensure you use WebGL for rendering to leverage GPU acceleration. 5. Implement efficient data parsing and rendering. Optimize your data parsing logic to minimize overhead. Use efficient data structures and rendering techniques for handling large volumetric datasets. Detailed instructions. 1. Update your pre-processing script. Ensure your pre-processing script handles compression and prepares the data for efficient transfer and rendering. Example Python script for compression. Python import nibable as nib, import numpy as np, import os, import json, import gzip. Def create slices and volumetric nifty file output dar img equals nib.load nifty file data equals img.get f data. Changes and optimizations. Summary. 1. Pre-processing enhancements, data compression. Compress volumetric data to reduce file size, which speeds up data transfer and loading times in the browser. Efficient storage. Save slices and volumetric data in a way that facilitates quick access and processing. 2. Efficient data handling and rendering. Optimized libraries. Use specialized libraries such as cornerstone.js and eniview.js designed for medical imaging to handle and render the data efficiently. WebGL and GPU acceleration. Implement WebGL for rendering to take advantage of GPU acceleration, ensuring smooth and fast visualization. Streaming and lazy loading. Implement techniques to load data incrementally or on demand, reducing the initial load time and allowing users to interact with data as it is being loaded. Workflow 1. 1. Pre-process MRI data. Compress and save the data in a format suitable for web transfer and quick access. Generate 2D slices and a 3D volumetric representation from the nifty file. 2. Optimize front-end code. Integrate libraries that specialize in medical image visualization. Update the rendering logic to utilize WebGL for performance improvements. Implement lazy loading or streaming of data to allow users to start interacting with the viewer before all data is fully loaded. Expected benefits. Faster loading times. Reduced file size and efficient data handling lead to quicker load times. Smooth interaction. GPU accelerated rendering ensures smooth panning, zooming, and navigating through the MRI data. Scalability. Incremental data loading makes the application more scalable and responsive even with large datasets. By implementing these changes and optimizations, your MRI viewer can achieve the performance and interactivity levels seen on platforms like openneuro.org.